Right, continuing with related rates here, let's read a person who is 6 feet tall is walking away from the base of a street light at a rate of 4 feet per second. Okay, so I've got a person who's walking away from the base of a street light. That's my stick street light. And we know that this person is always 6 feet tall, no matter what. That's not changing. Actually, this is one where when my son was in high school and he took AP Calculus, they had to do a project where they came up with their own. So you had to take like a classic problem and make it different. And what he did with a little bit of my help is when you're walking, typically your head kind of bobs up and down a little bit. So instead of this being a constant, it was like a sine wave instead, which made it a way more difficult problem, but it was interesting at least. All right. And the rate at which he's walking away from the street lamp. So I'm going to call this M for, I'll call it, it said a person. I shouldn't assume gender here. So it does say a person. So I'll call that P. And I know that dp dt is changing, or dp dt is always going to be, P is changing, but dp dt is always going to be 4 feet per second. Then it says the height of the street light is 16 feet. Since that's constant, go ahead and put it in. If it's something that's changing, use a variable for it. I've done ones like this where, it's a Jack and the Beanstalk problem where the light source is on something that's getting taller all the time. Okay? What is the rate at which the person's shadow lengthening? Okay, so where is the shadow going to be? Well, first of all, shadows are on the ground. You don't see the shadow until it hits the ground. So his shadow is going to be over here. And we want to know just at what rate is the person's shadow lengthening. And notice it doesn't give you a specific time. Well, that's kind of interesting. Let's see if we can find out what's going on here. So the reason I wanted to do this one is because it's a little different than the conical pile things that we've been doing, because there's no volume involved here. But notice we have two triangles, this small triangle with the 6 and the S, and this great big triangle with the 16 and the S and the P. Those two triangles are similar to one another. So that's going to be what relates my variables here. S is to 6 in the same way as what is to what in the big triangle. Yeah, S plus P is to 16. Now, we could take the derivative with respect to time right now. It's a lot easier actually if you multiply or cross multiply here to get rid of the fractions. So that'll be 16s is equal to 6s plus 6p. Well, I can simplify that even more, right? 10s is going to be equal to 6p. Now I'll take the derivative of both sides with respect to time. And I'll have 10 ds dt is equal to 6 times dp dt. Well, I know dp dt, so I'll substitute that in. 10 ds dt equals 6 times 4. So ds dt is going to be, that's 24 divided by 10, is 2.4 feet per second. So no matter where he is, his shadow is going to be lengthening at the same rate. Okay, and again, there's all kinds of variations on this problem where, the man is getting taller, or the street lamp's getting shorter, or all kinds of other things. Sometimes this distance is constant, but one of these other two things is changing. They're all fairly similar, and some of them are harder and some of them are easier. This actually turns out to be, in the end, one of the easier ones. But the idea is always the same. You want to set up a ratio, and be sure to use this whole side for the big triangle. That's the most common mistake, is that people will do 6 is to S as 16 is to P, which just isn't true. Okay, that's why I wanted to show you that one. I think you'll have one like that on tonight's assignment. So I wanted you to have seen one like that.